Second order covariation. Let's consider a glass of a cylindrical shape and let's assume that we are asked to sketch the height of the water contained in our glass with respect to time. Or again, to repeat the same exercise, this time with a bottle of a specific shape. Or that we have an inclined plane with a ball running along it and we are asked to sketch the graph of the distance traversed by the ball with respect to time. All the examples here described are examples of modeling of dynamic situation, and they require being able to represent one quantity as a function of another. So they require what is called covariational reasoning. This theoretical construct appeared for the first time in the theory of quantitative reasoning developed by Thompson. He states that a person reasons covariationally when she envisions two quantities' values as varying simultaneously. And again, Saldanha and Thompson's idea of covariation is of someone holding in mind an image of two quantities' values simultaneously, so that they have in mind a new object that is both the one and the other. The final version of this theoretical construct can be summed up in 6 levels of covariational reasoning, ranking from no covariation to smooth continuous covariation, and they have been developed by Thompson and Carlson. But let's return now to the example described previously, where we have the inclined plane and the ball running along on it. And let's assume that with time we have the possibility to change the inclination of our plane and to sketch again the graph of the distance traversed by the ball with respect to time. Well, the kind of reasoning required this time is something more complex than what is been described before. Specifically, we are not just asked to covary two variables, so what is called first-order covariation, in agreement with Thompson and Carlson definition, but we are asked to covary a function with a variable and specifically a parameter, what we call second-order covariation, which means the reasoning in terms of families of function. Introducing this more complex form of covariation requires enlarging the existing framework, and as Ferdinando Arzarello suggested, consider covariation as a larger form of reasoning, considering mathematical objects together with their mutual relationships. And specifically, a possible didactical counterpart of this covariation is called instrumented covariation, because activities designed with technological supports constitute an instrumentation of covariational processes. Here we provide a formal definition of what we call second-order covariation, which find a positive feedback in the definition of a second-order function, which can be found in the literature and have been provided by Vladimir. It refers to second-order covariation to functions whose argument is a parameter and their corresponding values are equations of function. So we state that mathematically, second-order covariation is expressed through one or more parameters in a family of functions, all modeling the same phenomenon. Our research aim is to enlarge and connote the covariational construct, both on a cognitive, mathematical, and didactical level. We aim to include second-order covariation in a coherent construct, and we are looking for multimodal markers connoting the different cognitive levels of reasoning. So the work is in progress. Thanks for your time and attention.